Right now, something invisible is pressing against every particle in your body. You cannot feel it, you cannot turn it off, and without it, every atom you are made of would fly apart at the speed of light in under a second. It is called the Higgs field, and physicists just realized it might be broken. We will go inside the machine colder than outer space, visit the particle that exists for less than a trillionth of a second, and stand at the edge of a discovery that could rewrite every law of physics we know. If you enjoy the journey, subscribe and leave a like. Let's begin. Most people picture space as a giant empty room, dark, cold and hollow, a place where nothing exists between the stars. That picture is wrong. Even in the deepest part of space, far from any planet, far from any star, something is there. You cannot see it, you cannot touch it. Instruments cannot measure it directly, but it fills every inch of the universe, from the inside of your bedroom to the edge of the observable cosmos. Scientists call it a quantum field, and one of these fields is unlike anything else ever discovered. It is called the Higgs field, and it never, ever turns off. Every other fundamental field in physics drops to zero energy when nothing is disturbing it. Gravity weakens with distance. Electric fields fade when charges are removed. The Higgs field does the opposite. It maintains a constant, non-zero energy level everywhere, at all times, no matter what. Even in a perfect vacuum with every particle stripped away, the Higgs field hums at full strength. It is baked into the fabric of the universe itself. Picture the ocean floor, even at the very bottom, where no fish swim and no light reaches. Pressure is everywhere. It presses on every surface equally, constantly, with no gaps. The Higgs field works the same way, except it presses on particles instead of surfaces. And unlike water pressure, it cannot be escaped by rising to the surface. There is no surface. The field extends forever. Here is what makes this genuinely strange. Scientists did not discover the Higgs field by seeing it. They discovered it by watching what it does to everything else. Particles that travel through it slow down. They drag. They resist motion in a way that bare particles in a field-free universe would not. That resistance is what we measure as mass. Without the Higgs field doing its job, electrons would have zero mass. Quarks would have zero mass. Every fundamental particle would race through space at the speed of light with nothing slowing it down. Atoms could never form. Chemistry would be impossible. Stars would never ignite. Life would never exist. The Higgs field is the reason anything physical can exist at all. For most of human history, scientists had no idea it was there. The concept appeared in theoretical equations in the early 1960s, but equations alone do not prove something exists. Physicists needed hard evidence. They needed to see the field do something visible, something they could measure in a laboratory. And that search would take 50 years, cost billions of dollars, and require building the most complex machine ever constructed by human hands. But the field itself is only half the story. The deeper mystery is what the field does to our understanding of physics. The same equations that describe the Higgs field also predict something terrifying. They suggest the field might not be sitting at its lowest possible energy. They suggest it could be unstable, a weighting trap, enormous in scale, that the entire universe is balanced on top of. That possibility has a name, and when physicists talk about it in private, they do not laugh it off. The story of the Higgs field starts as a triumph, but the further scientists look into it, the stranger it gets. And the next layer, the question of why particles have mass at all, breaks open something even harder to explain. Mass feels obvious. You are made of matter. Matter has weight. Weight comes from mass. Simple, except none of that explains where mass actually comes from. For most of physics history, mass was just treated as a fixed property of each particle, like a label stuck on at the factory. An electron weighs this much, a proton weighs that much. Nobody asked why. The number was measured, recorded, and accepted. Then, in the 1960s, a group of physicists started asking the uncomfortable question: why does any particle weigh what it weighs? Where does mass come from in the first place? The answer they found changed everything. Mass is the result of a constant interaction. Every particle that has mass is continuously dragging through the Higgs field as it moves through space. The field pushes back. That resistance, that constant tug between the particle and the field, is what we measure on a scale. More resistance means more mass. Less resistance means less mass. Think of it like walking through a crowded school hallway. If everyone knows you, they stop you every few steps. Your progress slows down. A kid nobody recognizes walks straight through without a single interruption. The crowd is the Higgs field. The popular kid is a heavy particle. The unknown kid is a photon, a particle of light, which does not interact with the field at all and flies through the universe at top speed with zero mass. That is a real, confirmed scientific mechanism. The Higgs field is what separates massless particles from massive ones. Now here is where it gets strange. The interaction between a particle and the Higgs field is not the same for every particle. Different particles feel the field with different strength. An electron, which is very light, interacts with the field weakly. A top quark, the heaviest fundamental particle scientists have found, interacts with the Higgs field with enormous strength. That variation in coupling strength is why particles end up with such wildly different masses. Nobody fully understands why the coupling strengths are what they are. The numbers fit the measurements. But the reason for those specific numbers? Unknown. The standard model of physics records them. It does not explain them. And that gap, that missing explanation, is one of the deepest unsolved problems in all of science. There is also a second mystery hiding inside this mechanism. The Higgs field gives mass to the fundamental particles, the electrons, the quarks, the basic building blocks. But most of the mass in your body does not actually come from this interaction. When quarks bind together to form protons and neutrons, the energy of that binding process contributes far more mass than the quarks themselves bring. About 99% of your body mass comes from nuclear binding energy, the force holding your atoms together. Only around 1% comes directly from the Higgs field. You are mostly made of energy that has been frozen into the shape of matter. Physicists call this one of the most mind-bending facts in modern science, and they mean it. The very thing you stand on, the chair beneath you, the floor beneath that, is almost entirely compressed energy held in place by forces. The Higgs field provides the spark. But the bulk of physical reality is something else entirely. What particles completely skip the field? That answer reveals something even more fundamental about how the universe is organized. Not every particle drags through the Higgs field. Some of them race straight through it, as if the field does not exist. Photons are the most familiar example. A photon is a particle of light. It moves at the fastest speed possible in the universe, roughly 186,000 miles per second. It can travel from the sun to Earth in about 8 minutes. And it never slows down, because it never interacts with the Higgs field. Zero coupling. Zero mass. Maximum speed. Gluons are the same. Gluons are the particles responsible for holding atomic nuclei together, carrying the strong nuclear force between quarks. They are fundamental, they are everywhere inside matter, and they also have zero mass. They also skip the Higgs field entirely. So the universe has two categories: particles that feel the field and gain mass, particles that skip the field and remain massless. And the line between those two categories determines almost everything about the structure of matter and energy. Here is why that line matters so much. Massless particles are forced to travel at the speed of light. Physics allows no other option. A massless particle cannot be at rest. It cannot be slowed. It must always be moving at full speed. The moment any particle gains even a tiny amount of mass from the Higgs field, it drops below the speed of light and becomes a different kind of thing entirely. It can stop. it can combine, it can build structure. Mass is what turns racing particles into matter. The W and Z bosons offer the clearest illustration of this. These particles carry the weak nuclear force, the force responsible for radioactive decay inside atoms. Before the Higgs field switched on in the early universe, the W and Z bosons were massless, just like photons. They flew freely at the speed of light, and the universe looked completely different. Then the Higgs field activated. The W and Z bosons started interacting with it. They gained mass, enormous mass compared to electrons. They slowed down. The weak nuclear force became weak, short-ranged, and confined to tiny distances inside atomic nuclei. The Higgs field literally reshaped the forces of nature by giving mass to the particles that carry them. Scientists confirmed the W and Z bosons gained mass through the Higgs mechanism long before the Higgs boson itself was found. The masses matched the predictions. That indirect evidence gave physicists enormous confidence the field was real. Still, confidence is not proof, and this raises one of the stranger tensions in modern physics. The photon and the gluon both skip the field, but they are completely different in every other way. The photon travels across the entire observable universe and can be detected with your eyes. The gluon is trapped permanently inside atomic nuclei and can never travel more than a tiny fraction of an inch on its own. Two massless particles, two wildly different behaviours. The Higgs field explains the mass. It does not explain why these particles interact with everything else so differently. That gap points toward forces and rules that the current framework cannot account for, and the particles that do feel the field, their exact masses carry a secret that physicists are still trying to crack. The next piece of this puzzle is the one number that holds everything together. Physics runs on numbers, constants, ratios, measurements that show up in equations and describe how the universe behaves. Most of these numbers can wobble a little without breaking everything. But one number connected to the Higgs field has almost no room to move at all. It is called the vacuum expectation value. That phrase sounds complex, so strip it down. Every field in the universe has a resting state, an energy level it settles at when nothing is disturbing it. For most fields, that resting state is zero. The Higgs field rests at a specific non-zero energy level. That level is its vacuum expectation value, and it determines how strongly the field pushes back against every particle in the universe. The measured value sits at around 246 billion electron volts of energy. That number sets the mass of every fundamental particle that interacts with the field. Change it, and you change the mass of every electron, every quark, every massive particle in existence. Now imagine turning that number down slightly. Even a small reduction would make electrons lighter. Lighter electrons would orbit atomic nuclei in larger, looser clouds. Chemical bonds would change. Atoms as we know them would not hold together in the same way. Life as we know it would be impossible. Now imagine turning the number up. Heavier electrons would collapse into tighter orbits, too close to their nuclei to form stable bonds with other atoms. Again, chemistry fails. Again, no life. The universe requires this number to land inside a tiny, specific range. And it does. Exactly. Physicists have no explanation for why. This is called the fine-tuning problem. The Higgs field's vacuum expectation value appears to be calibrated with precision that goes far beyond coincidence, and yet the current laws of physics offer zero mechanism to force that calibration. No equation predicts this number from first principles. Scientists measure it, they plug it in, they get results that match the universe they see. But the reason it is that number, and not something wildly different, remains completely open. Some physicists find this deeply unsatisfying. A law of physics should be derived, not just measured. If you cannot derive a number, you have not fully understood the system. Others point to a more uncomfortable possibility. Maybe the number is fine-tuned because our universe is one of many. Maybe other universes exist with different vacuum expectation values, and life simply could not evolve in them to ask the question. This idea has a name and a controversy all its own, and it comes back later in a way that makes things far stranger. For now, the key fact is this. The Higgs field sits at a specific energy level that makes atoms, chemistry, and human beings possible. It has sat there for nearly 14 billion years. Scientists assume it will continue doing so. But recent calculations have introduced a crack in that assumption. A crack that, if real, would mean the field's current energy level is borrowed, not permanent. The universe may be stable. Or it may be waiting, finding out which required scientists to actually prove the field exists. And that story starts with a machine, a long hunt, and one of the strangest 50-year bets in the history of science. Peter Higgs was a quiet physicist working at the University of Edinburgh in 1964. He was not famous. He had published only a handful of papers, but that year he sat down and worked through a set of equations describing how particles could gain mass without breaking the symmetry rules that governed all of physics at the time. His answer pointed to a field, and that field, his equation said, had to come with a particle. A ripple in the field that could, under the right conditions, be detected. He wrote up his findings and submitted them to a physics journal. The journal rejected the paper. The editor thought the ideas were too speculative and not relevant enough to physics. Higgs revised it, added a section specifically describing the particle, and resubmitted it to a different journal. It was accepted. That particle, the one he added almost as a footnote, became the most hunted object in the history of experimental physics. The problem was energy. To create a Higgs boson, you have to excite the Higgs field by slamming particles together with enough force to produce a ripple. The ripple is brief, incredibly brief, but it shows up as a detectable signal. Getting enough energy into a small enough space required machines that did not exist in 1964, or in 1974, or in 1984. Physicists kept building bigger accelerators. Each generation of machine pushed closer to the energy threshold. Each machine found other particles along the way, confirming other predictions, but the Higgs boson stayed hidden. Decades passed. The particle stayed out of reach. By the 1990s, the search had become the central mission of particle physics. Labs in Europe and the United States were racing. A massive accelerator planned for Texas was cancelled by Congress in 1993 after billions had already been spent. The hunt stalled. Then, Europe committed. The European Organisation for Nuclear Research began construction on the largest scientific machine ever built. A circular tunnel 16.7 miles around, buried beneath the Swiss and French countryside. It took a decade to build. It cost billions. And in 2008 it switched on for the first time. Within days, a malfunction caused an explosion in one of the superconducting magnets. The machine shut down for over a year. The hunt paused again. When it finally ran at full power, it smashed protons together at energies never achieved before in a laboratory. Thousands of scientists monitored the collisions. The Higgs boson, when it formed, survived for less than a billionth of a trillionth of a second before disintegrating into other particles. Catching it meant reconstructing its existence from the debris it left behind. The hunt was not just about building a powerful machine. It was about building detectors sensitive enough to find a single signal buried inside 300 trillion collisions. For 48 years after Higgs published his paper, the particle bore his name but had never been seen. That changed on the 4th of July, 2012. And the moment of announcement was nothing like a quiet scientific report. The story of what happened that day and the man sitting in the lecture hall carries more weight than the physics itself. Before the discovery could happen, a machine had to exist that had never existed before. The Large Hadron Collider sits inside a circular tunnel, buried about 300 feet underground near Geneva, Switzerland. The tunnel runs for 16.7 miles, forming a loop beneath farmland and the foothills of the Alps. It crosses the border between France and Switzerland 8 times as it curves underground, invisible from the surface, humming with energy. Inside this tunnel, two beams of protons travel in opposite directions. Not one proton each, hundreds of billions of protons per beam, grouped into tight bunches and accelerated to just a hair below the speed of light. When the two beams cross inside specially built collision chambers, the protons smash together with concentrated energy so extreme that the collision briefly recreates conditions similar to those that existed a fraction of a second after the Big Bang. The machine has to be kept extraordinarily cold to function. The superconducting magnets that steer and focus the proton beams must operate at minus 456 degrees Fahrenheit. That is colder than the surface of Pluto, colder than almost anywhere in the known universe. The coldest regions of deep space sit at around minus 455 degrees Fahrenheit, which makes the interior of the Large Hadron Collider slightly colder than the void between the galaxies. Building something colder than outer space on Earth, and keeping it that way, required solving engineering problems that had never been solved before. The magnets inside the tunnel number over 1,000. Each one weighs around 35 tons and uses coils of superconducting wire that carry enormous electrical currents without any resistance. The slightest disruption, a tiny piece of metal debris, a small electrical fault, can cause a quench, where a section of magnet suddenly loses its superconducting state and dumps its stored energy in milliseconds. The 2008 accident that shut the machine down for over a year was exactly that. A faulty electrical connection caused a quench that released enough energy in an instant to vaporize metal and damage nearly 50 magnets. The engineering required to restart and safeguard the machine after that accident was itself a scientific achievement. When the protons collide at full power, the energy released at the collision point is staggering. The particles that emerge from these collisions are tracked by detectors the size of apartment buildings, containing millions of individual sensor channels. Two main detectors, each built by separate teams working in parallel so they could independently verify each other's results, monitored every significant collision around the clock. The detectors had to distinguish meaningful signals from background noise at a rate that no human could manage. Automated systems filtered out billions of unremarkable collisions per second and flagged only the tiny fraction worth examining. Even after filtering, the amount of data generated every year would fill millions of laptop hard drives. All of this was built, calibrated, tested, and operated by a team of over 10,000 scientists and engineers from dozens of countries. And still, after all of that, the signal they were looking for was almost invisible. The Higgs boson, when it formed, did not leave a single clean track. It decayed instantly into other particles, and those particles left overlapping trails in the detector. Finding the boson meant working backward from those trails and reconstructing something that existed for a vanishingly short moment. What the teams found buried in that noise was stranger and more beautiful than anyone expected, and the story of those 300 trillion collisions deserves its own chapter. The detectors were running around the clock by late 2011. Thousands of scientists were watching the data. The proton beams collided millions of times every second inside the detector chambers. Most of those collisions produced nothing remarkable. Familiar particles, familiar signals, events that had been seen hundreds of millions of times before. The Higgs boson was expected to appear roughly once in every 10 billion collisions. At that rate, finding even a handful of events required an almost incomprehensible volume of data. By mid-2012, the two detector teams had each collected results from hundreds of trillions of collisions. Each team worked entirely independently. They did not share their internal analyses with each other. The separation was deliberate. If both teams found the same signal without coordinating, it was far harder to explain away as a coincidence or a statistical fluke. The signal they were hunting appeared as a bump in a graph, particles of specific energies showing up slightly more often than random chance would predict. The bump is incredibly faint at first, barely distinguishable from random variation. Then, as more collisions are added to the dataset, the bump grows. The statistical confidence rises. At 5 sigma, the scientific community's standard for a discovery, the chance of the signal being a random fluctuation drops below 1 in 3 million. By the summer of 2012, both detector teams had crossed that threshold independently. On the 4th of July 2012, a press conference was called at the European Organisation for Nuclear Research headquarters in Geneva. The lecture hall was packed. Scientists who had spent their entire careers working toward this moment sat in rows. Cameras broadcast live around the world. Peter Higgs was in the audience, 83 years old, having waited 48 years for this day. The results were presented one team at a time. Graphs appeared on the screen. The bump was there. Clear, statistically undeniable. A new particle had been found with a mass of approximately 125 billion electron volts. It matched the predictions for the Higgs boson. The lecture hall erupted. Scientists who rarely show public emotions stood and applauded. Some had tears. Peter Higgs, sitting in the audience, reached up and wiped his face. The boson confirmed the field. The field confirmed the mechanism. The mechanism confirmed that mass is an interaction, not a built-in property. 50 years of theoretical work had just been proven with data. But what exactly was discovered that day? Most people assumed a particle was found. The truth is slightly more precise, and the distinction matters in ways that change how you understand everything that follows. The boson itself is a ripple, a momentary disturbance in the Higgs field. The particle is not the field, it is the evidence that the field exists and behaves the way the equations predicted. The boson forms, lives for less than a billionth of a trillionth of a second, then decays into other particles and disappears. It cannot be bottled. It cannot be stored. Scientists are not finding Higgs bosons lying around. They are creating disturbances in the field and watching what those disturbances do. That distinction becomes critical when you ask what the field itself is doing at every moment, everywhere in the universe, even when no one is looking. Because the field is doing something. Always, and what it might be doing on its own, without any prompting from a particle accelerator, is the next question. July 4th, 2012 was already a charged date. For American physicists, the date carried obvious weight. For the physics world broadly, it was the anniversary of nothing in particular. The date was chosen because it was a convenient point in the conference schedule. Nobody planned for it to become the most remembered day in particle physics since the discovery of the electron. Peter Higgs arrived at the lecture hall in Geneva as an old man who had lived almost his entire adult life in the shadow of an unverified idea. He first wrote about the field in 1964. He was 35 years old. He spent the next 48 years watching other physicists build careers testing his theory, building machines aimed at his prediction, and coming up empty. He had watched the American Super Collider project get cancelled in the 1990s, killing the best chance of a faster discovery. He had watched the Large Hadron Collider get damaged and shut down in 2008. He had told interviewers more than once that he was not certain he would live to see the result. He was 83 years old when he sat down in that lecture hall. The room was standing room only. Scientists packed every seat and filled the standing areas along the walls. A crowd outside the building watched on screens. The presentations began with the first detector team's results. Graphs appeared. The speaker walked through the data carefully, building toward the conclusion without stating it outright. The tension in the room was physical. When the 5 sigma confidence level was confirmed on screen, the audience broke. Applause started before the sentence was finished. People stood. Colleagues who had worked alongside each other for decades embraced. The second team's presentation followed, with the same result reached independently. Peter Higgs sat through it all with a face that cycled through expressions difficult to put words to. When the full significance landed, he reached up and wiped tears from his eyes. He turned to the colleague sitting beside him and said, quietly, that he had not expected to live long enough to see this. He received the Nobel Prize in Physics the following year alongside Francois Englert. one of the other physicists who had developed the theory independently in the same year. Higgs did not find out he had won the prize from a phone call or an email. He did not own a mobile phone. A former neighbour who spotted him on the street in Edinburgh told him. The story of Higgs himself is a portrait of what science actually looks like for the people doing it. Decades of sitting with an unproven idea. A quiet stubbornness, a refusal to abandon a theory just because it was not yet testable. The reward for that patience arrived exactly 1 year before his death in 2024 at the age of 94. The discovery on that day was celebrated as a finish line. The physics community declared the Standard Model complete, the final major piece confirmed, but within the data from those 300 trillion collisions, something was already showing up that did not quite fit the picture of a tidy ending. The Higgs boson was real. Its mass had been measured. And that mass was a problem. A quiet, serious problem that the press conference did not discuss. A problem that pointed not to a completed theory, but to a broken one. Most science headlines about the Higgs boson described it as the particle that gives mass to other particles. That phrase is everywhere. It is also slightly wrong. And the difference between what the boson is and what the field is matters more than most people realise. The Higgs boson is not a factory. It does not fly around the universe handing out mass to particles it passes. It does not carry the mass-giving force the way a photon carries light, or the way a gluon carries the strong nuclear force. The boson is a ripple. When the Higgs field gets disturbed by an extremely energetic collision, it briefly vibrates. That vibration takes the form of a particle, a temporary concentration of energy in the field that behaves like a localized object. The boson appears, exists for an almost immeasurably short moment, and then collapses back into the field by decaying into other particles. The field itself is doing all the actual work. The field is what every massive particle drags through at every moment. The field is what sets the mass of every electron and every quark. The field is what fills the entire universe continuously. The boson is just the proof that the field is real. Here is the best way to picture it. Imagine the surface of a still lake. That lake is the Higgs field. Throw a stone in and watch the ripple spread outward. That ripple is the Higgs boson. The ripple is real. You can see it. You can measure it. But the ripple is not the lake. The lake was there before the stone hit. The lake continues after the ripple fades. The stone caused a temporary disturbance in something that was already there. Physicists needed the stone, the boson, to prove the lake existed. Once found, the boson's own properties became the data. Its mass told scientists how strongly the field couples to itself. The decay patterns told scientists which other fields the Higgs field connects to. Each measurement fed back into the larger picture, and the mass of the boson, measured at around 125 billion electron volts, immediately created a serious conflict with theory. Here is why. Every particle in the universe is surrounded by quantum fluctuations. The vacuum of space is constantly producing tiny pairs of virtual particles that pop into existence and then annihilate each other in unimaginably short bursts. These virtual particles interact with the Higgs boson. Each interaction slightly shifts the boson's mass. When physicists calculated the total shift from all these interactions, the math predicted the boson's mass should be enormous, orders of magnitude larger than what was measured. The boson's actual measured mass is about 125 billion electron volts. The theoretical prediction for its raw mass, before the quantum corrections, is roughly 10 million billion electron volts. Something is cancelling out almost all of that predicted mass. Something is making the number drop to the measured value with extraordinary precision. Physicists call this the hierarchy problem. It has no accepted solution. It is one of the deepest open questions in all of physics. And it quietly reveals that the Standard Model, even at the moment of its greatest triumph, already contained a crack. What fills the vacuum that produces those fluctuations? What unknown force or particle is doing the cancelling? The answer might be hiding in the 1% of your body that comes directly from the Higgs field. Stand on a scale. Whatever number it shows, almost none of it comes from what you probably think it does. The atoms in your body are made of protons, neutrons, and electrons. The electrons are light, contributing almost nothing to the total. So the bulk of your mass comes from protons and neutrons. And protons and neutrons are made of quarks, so your mass must come from quarks, right? Here is the strange part. Add up the actual masses of the 3 quarks inside a single proton. You get a total that is less than 2% of the proton's actual mass. The quarks themselves contribute almost nothing to the weight of the proton. The remaining 98% comes from energy, specifically from the kinetic energy of the quarks moving around inside the proton at enormous speeds, and from the energy stored in the gluon field that holds the quarks together. That trapped energy, that whirling storm of motion and force, locked inside a space far smaller than an atom, is what gives protons and neutrons their mass. And protons and neutrons give you your mass. So when you step on a scale, you are mostly weighing the energy cost of holding your atomic nuclei together. Albert Einstein's famous equation describes exactly this relationship. Energy and mass are 2 forms of the same thing. The binding energy inside atomic nuclei has mass. It sits on a scale just like a rock or a brick. Humans were splitting and fusing atoms for decades before most people fully grasped what that equation was actually saying. The Higgs field contributes to the quark masses themselves, the small baseline mass that each quark carries before the binding energy is added. But that contribution, while essential for establishing the structure, is the small part of the total picture. Roughly 1% of your body's total mass comes from direct Higgs field interactions with fundamental particles. 1% sounds trivial, and in terms of quantity it is a small slice. But it is absolutely essential. Without the baseline mass the Higgs field gives to quarks and electrons, the nuclear forces could not bind them into stable structures at all. That 1% is the foundation. The other 99% is built on top of it. There is something quietly astonishing about this. The most tangible thing in your life, your physical body, the weight of your own hand, is primarily frozen energy. Ancient energy, locked in place since the first atoms formed in the early universe, now arranged into the specific shape of a person standing in a room. You are mostly an energy configuration that happens to feel solid. And here is the thing that physicists lose sleep over. All of that structure, all of that stable frozen energy depends completely on the Higgs field sitting at its current value. Change the field's strength, and every quark mass shifts. Shift the quark masses, and the nuclear binding energy recalculates. Recalculate the binding energy, and protons either fall apart or crush together. Either way, atoms as they exist right now stop working. Your physical existence is downstream of a number you cannot see, feel, or control. What happens to that existence if the field briefly turns off? The answer is as fast as it is total. 1% of your body mass comes directly from the Higgs field, interacting with fundamental particles. That fraction sounds like rounding error. It is closer to the hinge point of all physical existence. To understand why, you have to look at what that 1% actually does. It sets the baseline mass of electrons, and electron mass controls the entire structure of every atom in the universe. An atom works because electrons orbit a nucleus. The distance of that orbit, the size of the cloud the electron forms around the nucleus, depends directly on the electron's mass. A lighter electron forms a larger, more spread out orbit. A heavier electron collapses into a tighter orbit. The exact mass of the electron, set by its interaction with the Higgs field, determines how closely 2 atoms can approach each other and form a chemical bond. Chemical bonds are everything. They are the connections between atoms that create molecules. Water is a chemical bond. Proteins are chemical bonds. DNA is a chemical bond. Every biological structure, every material that exists, every compound that ever formed anywhere in the universe is the result of electron mass sitting at the exact value the Higgs field gives it. If the Higgs field's strength shifted by a small amount, electron mass would shift with it. The orbits would change. The bond distances would change. Molecules that currently exist would become impossible or would form at completely different sizes with completely different properties. Water might no longer be liquid at Earth's temperatures. Proteins might fold into shapes that cannot hold a biological function. Life as it currently exists would be erased and replaced with something unrecognizable, or nothing at all. This is what physicists mean when they describe the Higgs field's value as fine-tuned. The word fine-tuned, in this context, means the value is precisely in the range where the universe produces stable, structured matter. A small change in either direction breaks the chemistry. Nobody understands how the field arrived at this value. The equations describe how it behaves. They do not explain why it chose this particular strength. Some researchers have tried to calculate what a universe with a different Higgs field strength would look like. In a universe with a significantly weaker field, electrons would be so light they could barely stay bound to nuclei. Atoms would be enormous, fragile, barely coherent. In a universe with a significantly stronger field, electrons would be so heavy they would crash into the nucleus and destroy it. Either way, the periodic table as we know it ceases to exist. Our universe, the one with stable atoms and chemistry and biological complexity, requires the Higgs field to sit inside a very specific range. And it does. That precision, that exactness, is either an extraordinary coincidence or evidence of something deeper that physics has not yet found. Scientists debate both possibilities seriously. Neither side has proof. The mystery is fully open. And the mystery becomes more uncomfortable when you ask what would happen if the Higgs field were not just shifted slightly, but switched off entirely, instantly, with no warning. The physical consequences of that scenario are fast, total, and require no imagination to grasp. The numbers are enough. Imagine the Higgs field turning off right now. Every particle that interacts with it, every electron, every quark, every massive particle in the universe, instantly loses its mass. The entire mechanism stops. The timeline of what follows is shorter than any clock can measure. At the first instant, every quark inside every proton and neutron in your body becomes massless. Massless particles cannot remain bound inside a proton. The strong nuclear force still exists, but without mass to anchor the quarks in place, the internal structure of every proton and neutron collapses. Atomic nuclei disintegrate. The process takes roughly a 10,000th of a billionth of a billionth of a second. Your atoms are already gone. At the next instant, there are no more atoms. There are no more nuclei to hold electrons in place. Every electron in the universe, now also massless, accelerates to the speed of light. Every photon that was previously slowed by interactions now races freely. Every particle that previously had mass joins the universe of massless things, racing outward at the maximum possible speed in every direction. There is no explosion in the conventional sense. There is no heat, no fire, no shockwave. The matter simply ceases. Everything you are standing on, the planet itself, the star at the center of the solar system, every galaxy in the observable universe, converts from structured matter into a high-energy spray of massless particles radiating outward at the speed of light. The universe becomes a vast, featureless cloud of radiation with no structure and no possibility of structure forming again. This thought experiment sounds extreme, and the Higgs field is not switching off anytime soon. But the reason physicists take this scenario seriously is that the field's current energy level is, by some calculations, not the lowest energy level it could occupy. The field might be sitting in a temporary state rather than a permanent one. If it is temporary, then at some point in the future a random quantum event could push it toward a lower energy level. A lower energy level means a different vacuum expectation value. A different vacuum expectation value means different particle masses across the entire universe. The particles that exist right now, calibrated to the current field strength, would no longer match the new rules. Structure would dissolve. Physicists call the current state of the field a false vacuum. The universe may be stable. The universe may be balanced on top of a lower energy state that it has not yet fallen into. The height of the ledge and the probability of falling depend on measurements that scientists are still refining. The current estimate is that this event, if it happens at all, would occur on a timescale far longer than the current age of the universe, likely longer by many orders of magnitude. But the concept of a false vacuum is real physics. It is derived from the same equations that predicted the Higgs boson, and those equations currently leave room for the universe to be less stable than it looks. That instability has a name, a visual shape, and an expanding edge that travels faster than any warning could travel. And the description of what that expanding edge looks like when it arrives is one of the most unsettling ideas in all of physics. Before going deeper into what the field's instability means for the universe, it helps to understand one more layer of the field itself. Why some particles feel it strongly and others barely notice it at all. The difference comes down to a property called coupling strength. Every particle that interacts with the Higgs field has a specific coupling value. That coupling value determines how strongly the field resists the particle's motion, which determines how much mass the particle ends up with. The top quark has the highest coupling of any known fundamental particle. Its interaction with the Higgs field is so strong that it ends up with a mass roughly equal to an entire gold atom, despite being a single fundamental particle. It is the heaviest fundamental particle scientists have ever found. Its coupling to the field is close to 1, meaning it interacts with almost maximum strength. The electron has a very small coupling value. Its mass is tiny compared to the top quark, and the neutrino, a ghostly particle that passes through matter almost without interacting with anything, has an extremely small mass and an extremely small or possibly zero coupling to the Higgs field. Scientists are still measuring this. The crowded room picture makes this easier to hold in your head. Imagine a room packed with people. A well-known celebrity walks in. Everyone stops them. People cluster around them, slowing their progress, making them work to cross the room. That resistance to motion is mass. The celebrity is a top quark. Now a stranger walks in. Nobody knows them. They walk straight through the crowd without anyone stopping them. That is an electron, lighter, less coupled, less slowed by the field. Now someone who is completely invisible walks through. No one sees them at all. That is a photon. Zero coupling. Zero mass. Maximum speed. The crowd is the Higgs field. The people in the room are the field's constant energy, and the variation in how much each particle gets stopped by that crowd is what produces the wide range of masses observed across all the fundamental particles. This picture has a real name in physics. It is sometimes called the Higgs mechanism, illustrated as a social force. Scientists use it specifically because it captures something real. The field does not check what kind of particle is passing through and decide consciously how hard to push. The coupling strength is an intrinsic property of each particle, built into the equations that describe it. The field simply exerts the interaction that the coupling demands, and the full range of coupling strengths, from 0 for photons up to nearly 1 for the top quark, spans an enormous gap. Scientists do not know why the couplings take the specific values they do. The standard model records those values from experiment. It does not derive them from deeper principles. This is a pattern that keeps appearing. The standard model measures and describes. It does not explain origins. The couplings are what they are. The field strength is what it is. The boson mass is what it is. Every one of these measured constants has no theoretical derivation from first principles. That gap between measurement and understanding is exactly where physics begins to break down. And the next place that breakdown becomes impossible to ignore is in the equations for the boson's own mass, where the numbers produced by the standard model are so wildly wrong that physicists know something major is missing. Every force you can name comes with a direction. Gravity pulls down. A magnet pulls left or right depending on which pole is facing you. Electric fields push charged particles toward or away from each other along a line. Even the weak nuclear force has a preferred direction built into its structure. All of these are vector fields. They have both a strength and a direction at every point in space. The Higgs field is different. It is a scalar field. That single word, scalar, separates it from every other fundamental field in physics and shapes everything about how it works. A scalar field has only a value at each point in space. No arrow, no direction, just a number. The temperature in a room is a scalar field. Every point has a temperature, but the temperature does not point anywhere. The Higgs field works the same way. Every point in the universe has a Higgs field value, but the field itself has no orientation. This matters for a specific reason. Vector fields can cancel each other out when two fields push in opposite directions. Two magnets can be arranged to neutralize each other. Two electric fields can be set up to sum to zero. The Higgs field has no direction to cancel. It cannot be shielded. It cannot be blocked. There is no configuration of any other field that reduces the Higgs field to zero in any region of space. Every point in the universe at all times sits inside the full strength of the Higgs field with no exceptions and no way to opt out. The scalar nature also means the Higgs field interacts very differently with particles than other fields do. A magnetic field interacts with a particle based on the particle's charge and the direction it is moving. The Higgs field interacts based purely on the particle's intrinsic coupling value. Spin does not affect it. Charge does not affect it. Direction of motion does not affect it. The coupling is the only variable. This produces a field that is simultaneously one of the most universal things in physics, and one of the strangest. Universal because it affects every massive particle everywhere without preference. Strange because it operates through a mechanism that has no analogue in human experience. You have felt magnetic attraction and electric shock. You have never directly felt the Higgs field, yet it is the reason you have mass. The scalar nature also played a key role in how the field was theorized in the first place. In the 1960s, physicists were struggling with a mathematical problem. Giving mass to particles in certain equations automatically broke the symmetry rules that made those equations work. Peter Higgs and others showed that a scalar field with a non-zero vacuum value could give mass to particles without breaking the underlying symmetry in a harmful way. The symmetry was hidden, not destroyed. That mechanism, hiding symmetry rather than breaking it, is one of the most elegant ideas in modern physics. It solves a problem that looked mathematically unsolvable, and it does so by using exactly the kind of field that has no direction, only a value. The field is everywhere, always, directionless, and constant. And at a certain energy level, that constant value creates a universe that can hold atoms, planets, and people. But what happens when that energy level itself turns out to be mathematically unstable? That question leads directly to one of the most troubling predictions the Standard Model has ever made. Every field settles somewhere. Electric fields rest at zero when no charges are present. Gravitational fields drop to their lowest point. The Higgs field settles at a specific energy level that is not zero. It sits higher than zero, constantly, everywhere. And that specific level changes everything. Physicists call this the vacuum expectation value. Strip that phrase down to its core meaning, it is the value the Higgs field holds in a completely empty vacuum. No particles, no radiation, no disturbance of any kind, pure emptiness. And even there, the Higgs field maintains a constant non-zero energy. That energy level is not arbitrary. It is the exact value that gives electrons, quarks, and other massive particles their specific masses. If the vacuum expectation value were different, every particle mass in the universe would shift. The entire structure of matter would reorganize around the new number. The The measured value is about 246 billion electron volts. That number was not predicted. It was discovered by working backward from the measured masses of fundamental particles and plugging values into the equations until the math matched reality. The number fits. But where it comes from, why it is this value and not any other, remains without an explanation. Picture a valley between two mountains. The lowest point of the valley is where a ball naturally comes to rest. That resting point is 0 for most fields. But for the Higgs field, the landscape of energy has a strange shape. The very centre of the valley, the point that looks like the lowest spot, is actually a small hill. The true lowest points are displaced to either side. The field settles at one of those displaced low points, not at the centre. This shape of the energy landscape has a name in physics: the Mexican hat potential. Imagine a sombrero lying flat. The brim, slightly lower than the raised centre, is where the Higgs field comes to rest. The field slides off the central peak and settles somewhere on the brim. Every direction around the brim is equally low in energy. The field picks one, and the universe locks into that choice. This choice, this spontaneous settling at a non-zero value, is what physicists call spontaneous symmetry breaking. The underlying equations are perfectly symmetric. Every position on the brim is equivalent, but the field must pick one position. Once it does, the symmetry of the equations is hidden inside the structure of the field rather than expressed openly. This is not a flaw in the theory. Spontaneous symmetry breaking is what allows the field to do its job. The non-zero vacuum value is the mechanism by which particles gain mass. The broken symmetry is the source of the field's power, and once the field's settled, it has stayed settled for nearly 14 billion years. The universe has been running on this vacuum expectation value since moments after the Big Bang. The atoms, the stars, the planets, you, are all downstream of that original settling. But settled does not necessarily mean stable. The valley the field settled into might be real, or it might be a dip in a hillside above an even lower valley below. If a lower energy state exists, the field sitting at its current value is called a false vacuum. And a false vacuum, in physics, comes with a clock. Nobody knows for certain if the clock is running, but the equations that best describe the field suggest it might be. 2012 was the year particle physics declared victory. The Higgs boson was found. The last missing piece of the standard model was confirmed. Textbooks that had contained the boson as a prediction for decades could finally describe it as a discovery. Physicists around the world celebrated a theory that had been built over half a century and now appeared complete. Except it was not complete. The crack had been visible in the equations for years. The discovery of the boson did not close it. If anything, the discovery made it harder to ignore. The standard model describes particles as existing inside a universe filled with quantum fluctuations. The vacuum of space constantly produces pairs of virtual particles that pop in and out of existence. These virtual particles interact briefly with real particles, including the Higgs boson, and those interactions shift the boson's mass slightly. Each interaction contributes a small correction to the mass. When physicists calculate the total effect of all those corrections, the math produces a number, and that number is catastrophically larger than the measured mass of the boson. The corrections stack up. Every known particle in the standard model contributes a quantum correction to the Higgs boson's mass. Each contribution adds a large number. When you sum them all, the theoretical prediction for the boson's raw mass reaches a value roughly 10 million billion electron volts higher than what is measured. The measured mass is around 125 billion electron volts. The theory predicts corrections that should push the mass to an astronomically larger number. Something is cancelling out almost all of those corrections, leaving behind the small measured value. For those corrections to cancel this precisely, the cancellation must be accurate to roughly 30 decimal places. 30, the number that emerges from the theoretical equations and the number measured in the laboratory agree, but only because something is deleting an enormous theoretical contribution from the calculation. No one knows what is doing the deleting. This is called the hierarchy problem. It is one of the most studied, most debated, and least resolved puzzles in all of physics. Hundreds of papers have been written about it. Entire theoretical frameworks have been developed to try to solve it. Experimental programs costing billions have been designed to find the particle or force responsible for the cancellation. So far, none of them have found anything. The standard model does not even attempt to explain the cancellation. It simply accepts the measured value and plugs it into the equations. The gap between the theoretical prediction and the measured reality is acknowledged, named, and left open. For a theory that successfully predicted the existence of dozens of particles and explained the behaviour of 3 of the 4 fundamental forces, this is a glaring gap. The standard model is the most tested and accurate theory in the history of science, and it contains, right at its centre, an enormous number that it cannot explain. The most popular candidate for the explanation involves a class of theories that predict a whole new category of particles. These particles would interact with the Higgs boson in a way that cancels the quantum corrections naturally, without requiring precise fine-tuning. The theory is elegant. The predicted particles have specific properties, and for over 40 years, physicists have been searching for them. They have found nothing. And that absence is the next crisis. The hierarchy problem has a favourite solution. It is called supersymmetry, and it works like this. Every particle in the standard model has a partner, a shadow version with different spin properties. Electrons have selectrons. Quarks have squarks. The Higgs boson has multiple Higgsino partners. These partner particles, called superpartners, interact with the Higgs boson through quantum corrections the same way normal particles do. But the corrections from superpartners have opposite signs. When you add the correction from a particle and the correction from its superpartner, they cancel. The enormous number that the hierarchy problem points to gets wiped out naturally, not by coincidence, but by the mathematical structure of the theory itself. The Higgs boson mass stays small because the cancellations are built in. Supersymmetry is not a wild guess, it is mathematically elegant. It solves the hierarchy problem cleanly. It also, as a bonus, predicts that the lightest superpartner particle would be stable, invisible, and have mass. That description matches every known property of dark matter, so supersymmetry would simultaneously solve the hierarchy problem and explain what dark matter is. It would be one of the most powerful theoretical achievements in physics if it were true. The problem is 40 years of experimental silence. Superpartner particles, if they exist, have specific mass ranges predicted by the theory. The Large Hadron Collider was built, in part, to produce these particles. If supersymmetry is correct, the machine should have seen superpartners already. The energy levels explored by the collider are squarely inside the range where the lightest superpartners were expected to appear. The detectors have found nothing. Every experimental search for superpartner particles has come back empty. Each time the search finds nothing, the lower bound on the mass of those particles is pushed higher. Higher masses mean more fine-tuning is required to keep the theory working, which makes the theory less natural and less compelling. Physicists who spent their careers developing supersymmetry have watched the experimental constraints tighten year after year. Some have abandoned the framework, others argue that superpartners are simply heavier than current machines can reach. A future collider, more powerful than the Large Hadron Collider, might still find them. But if superpartners exist at very high masses, their cancellation of the quantum corrections to the Higgs mass becomes less perfect. The hierarchy problem returns, partly solved at best. Other proposed solutions exist. Some theories predict extra dimensions of space, curled up so small they are invisible at normal scales. These extra dimensions could dilute the enormous quantum corrections by spreading them across multiple dimensions, leaving a smaller residual value. Other frameworks involve entirely new symmetry principles unrelated to supersymmetry. Some theorists have even suggested the Higgs boson is not fundamental, but is instead made of even smaller components, called composite models. Every proposed solution makes predictions. Every prediction has been tested. Every test has so far returned empty hands. The Higgs boson mass remains measured at around 125 billion electron volts. The theoretical correction that should push it astronomically higher remains calculated and uncontested. The cancellation that keeps the measured value small remains completely unexplained. This is where the standard model stands. A theory that predicted every particle it described with extraordinary accuracy, confirmed in thousands of experiments, producing results that match reality to dozens of decimal places, and at its centre, a number it cannot explain, pointing directly toward physics that does not yet exist. And that unknown physics, whatever it is, may connect directly to the strangest threat the universe faces. A threat that does not come from outside, it comes from inside the field itself. The hunt for superpartners did not begin quietly. It began with confidence. When the Large Hadron Collider switched on in 2008, the physics community expected results fast. Supersymmetry had been the leading candidate solution to the hierarchy problem for decades. The math was solid. The predictions were specific. Theorists had calculated the masses at which superpartners should appear, and those masses sat well within the energy range the new machine could reach. Experimentalists prepared their detectors for the signatures. A superpartner particle, once created in a collision, would decay into lighter particles plus the stable, invisible lightest superpartner, which would escape the detector without leaving a trace. That missing energy, a collision where the numbers do not add up because something invisible carried energy away, was the fingerprint to find. The machine ran. Collisions happened by the billions. The missing energy signature was hunted in every dataset. Year after year, nothing appeared. By 2012, when the Higgs boson was confirmed, the absence of superpartners was already becoming a serious problem. The simplest versions of supersymmetry, the ones that required the least fine-tuning and solved the hierarchy problem most cleanly, predicted superpartners in a mass range the collider had already fully explored. Those versions were statistically excluded. Dead, theorists responded by constructing more complicated versions of supersymmetry that pushed the superpartner masses higher. Higher masses meant the collider might simply need more energy to reach them. The theory survived, technically, by retreating to heavier predictions. But heavier superpartners create a different problem. If the superpartner masses are very high, their cancellation of the quantum corrections to the Higgs boson mass becomes imprecise. A small residual mismatch remains, and that mismatch brings back a version of the hierarchy problem the theory was supposed to eliminate. The solution becomes less elegant with each upward revision of the mass predictions. By 2024, after the collider had run through multiple upgrade cycles and explored energies far beyond its original design, the superpartner mass limits had been pushed to levels that most theorists considered extremely uncomfortable for the framework. Thousands of collision datasets, analysed by hundreds of physicists, had found no trace of any superpartner. The theory remains mathematically valid. Superpartners could still exist at masses beyond current reach. A more powerful collider might find them. Several proposals for next-generation accelerators, with energies several times greater than the current machine, have been developed specifically to continue this search. But the silence so far has forced a reckoning. A theory that was considered almost certain to be confirmed has spent 4 decades producing no experimental evidence. The physics community has split. Some researchers remain committed to supersymmetry. Others have concluded that the absence of evidence at this scale is itself a form of evidence, and that the hierarchy problem requires a fundamentally different kind of answer. Some of those alternative answers point to places in physics that are even harder to test. Places that challenge the basic assumption that science must make predictions about things that can be measured in a laboratory, and one of those places connects directly to the question of why the Higgs field has the strength it does, and whether the answer to that question might lie entirely outside the observable universe. There is a particle that passes through your body at a rate of about 65 billion per square inch every second. You feel none of them. They interact with almost nothing. They travel through the entire Earth the way light travels through glass, barely slowing down. These are neutrinos, and they represent one of the deepest unsolved conflicts in the physics of the Higgs field. The Standard Model originally predicted neutrinos to be massless. The equations worked cleanly with that assumption. Massless neutrinos would not interact with the Higgs field, just like photons. They would be permanent members of the zero mass category, racing through space at the speed of light, invisible and structureless. Then experiments deep underground changed the picture entirely. Neutrinos come in three types, called flavors: electron, muon, and tau. Physicists discovered in the late 1990s and early 2000s that neutrinos oscillate between these flavors as they travel. An electron neutrino produced in the Sun might arrive at Earth partially converted into a muon neutrino. This flavor oscillation is only possible if the different neutrino types have different masses, and different masses means some mass must exist. Neutrinos have mass, small mass, almost incomprehensibly small mass, but real, measured, confirmed mass. This broke the Standard Model's prediction. The equations had to be patched to accommodate the new data. The patch worked mathematically, but it raised an immediate question: where does neutrino mass come from? For other massive particles, the answer is the Higgs field. The particle couples to the field. The field gives resistance. The resistance becomes mass. But neutrino masses are so extraordinarily small, billions of times smaller than the electron mass, that many physicists suspect the Higgs field alone cannot explain them. The coupling required would have to be absurdly tiny, far smaller than any other coupling measured in nature. That level of smallness seems unnatural in the same way the Higgs boson mass fine-tuning seems unnatural. One popular alternative is called the seesaw mechanism. It proposes that there exist extremely heavy partner particles for the neutrinos, so heavy that they have never been produced in any collider and may never be reachable by any machine humans could realistically build. The existence of these heavy partners would mathematically drive down the masses of the ordinary light neutrinos to the tiny values observed. A seesaw, one end goes up, the other goes down. The seesaw mechanism is mathematically elegant. It solves the smallness of neutrino mass without requiring an unnaturally tiny coupling. But the heavy partner particles it predicts, called right-handed neutrinos, have never been detected. Their predicted masses may be so high that they are permanently beyond experimental reach. This is a recurring theme in the physics of the Higgs field. The best theoretical solutions to its mysteries make predictions about particles or energy scales that current or near-future experiments cannot access. The theory points somewhere real, but the evidence remains just out of reach. Neutrino mass is confirmed. Its source is unknown. The seesaw is compelling. It is untested. And neutrinos carry one more mystery on top of this one, a mystery that connects them to the reason matter exists at all, and to one of the Higgs field's strangest possible roles in the early universe. Something is holding galaxies together that scientists cannot see. When astronomers calculate how much gravity a galaxy should produce, based on the visible matter inside it, stars, gas, dust, they get a number. Then they measure how fast stars at the outer edges of the galaxy are actually moving. A star moving too fast for the gravity it experiences should fly off into space. Stars at galactic edges are moving far too fast to be held by the gravity of visible matter alone. And yet they stay. Something with mass, something that exerts gravity, is present in enormous quantities around every galaxy in the observable universe. Scientists call it dark matter. It makes up roughly 27% of the total energy content of the universe. All the visible matter, every star and planet and cloud of gas, accounts for only about 5%. Dark matter has mass. Anything with mass interacts with the Higgs field. This means dark matter particles, whatever they are, almost certainly have some relationship with the Higgs mechanism. they must couple to the field at some level. That coupling would leave a detectable fingerprint. For decades, physicists have been trying to catch that fingerprint. The most direct approach is underground detection. Experiments buried deep beneath mountain ranges or former mines shield their detectors from cosmic ray interference and watch for the rare moment when a dark matter particle collides with an atomic nucleus. The collision would produce a tiny, measurable recoil. Despite enormous detectors and years of observation, no confirmed dark matter signal has been recorded. The collider approach is the second strategy. If dark matter particles couple to the Higgs boson, then creating Higgs bosons in the Large Hadron Collider might sometimes produce dark matter particles as the boson decays. A dark matter particle in a detector would carry energy away invisibly. That missing energy pattern was part of what collider physicists searched for. So far, the searchers have found no confirmed signal. The astrophysical approach looks for the products of dark matter annihilation in space. If two dark matter particles collide and destroy each other, the energy released might produce gamma rays or other detectable radiation. Telescopes have scanned regions where dark matter density should be highest, including the galactic center. Some interesting signals have been found. None have been definitively confirmed as dark matter. Every search method has come up empty. Dark matter remains the largest known component of matter in the universe, and scientists do not know what it is, what particle it corresponds to, or how strongly it couples to the Higgs field. They know it has mass. They know mass requires a coupling. They cannot find the coupling. The frustration among experimental physicists working on this problem is real. Decades of increasingly sensitive experiments have narrowed the range of possible properties for dark matter particles, but the core mystery has not moved. The particle is somewhere in the ruled-out space getting smaller, but the answer has not arrived. And dark matter, massive and invisible, sitting in enormous quantities around every galaxy, may be doing something else entirely. Something that connects it to the stability of the Higgs field and the question of whether the universe is sitting on a trapdoor. That trapdoor has a name, and its description is the most viscerally unsettling idea in modern cosmology. The Higgs field sits at a specific energy level. That level is not zero. It is the non-zero value that gives particles mass and makes the universe work. For almost 14 billion years, the field has held at this level with no sign of moving. You might assume that means it is stable. Physicists are no longer sure. To understand the problem, go back to the energy landscape of the Higgs field. Picture a ball sitting in a bowl. The lowest point of the bowl is the stable resting position. If you nudge the ball, it rolls back. That is true stability. The ball is at its absolute lowest energy, and any small disturbance just sends it back to the center. Now picture a different landscape. A ball sitting on a wide, flat plateau with a small dip in the middle. The ball sits in the dip. It feels stable. Small nudges do not push it out. But the plateau has an edge. And beyond the edge is a much deeper valley below. The ball is stable against small disturbances. Against a large enough push, it would roll to the edge and fall. The current state of the Higgs field may be the dip on the plateau. Physicists call this a false vacuum. The field is locally stable, meaning it resists small disturbances, but it is globally unstable, meaning a deep enough energy state exists below its current level. If the field ever dropped to that lower state, every particle mass in the universe would recalculate to match the new vacuum expectation value. The laws governing atomic structure would change instantly and permanently. For many years, physicists debated whether the Higgs field was in a true vacuum or a false vacuum. The answer depended on two measured numbers, the mass of the Higgs boson and the mass of the top quark. Both were measured precisely after 2012. When those measured values were plugged into the stability equations, the result came back in a region called metastability. The Higgs field is stable on any timescale relevant to human experience or even to the current age of the universe. The estimated time before a false vacuum decay event would occur naturally runs into numbers so large they require scientific notation to write. But metastable is not the same as stable. Metastable means the field is in a temporary resting state. Given enough time, or a large enough random quantum fluctuation, the field could tunnel through the barrier, separating its current state from the deeper energy level below. The word tunnel here is technical. In quantum mechanics, particles can pass through energy barriers they classically should not be able to cross. This is called quantum tunneling. It happens constantly at the subatomic level. It powers the nuclear fusion inside the Sun. Applied to the Higgs field, it means the field does not need a massive external push to escape its current state. Given a long enough timeline, random quantum fluctuations could do the job spontaneously. The probability per unit volume per unit time is extremely small. But the universe is enormous and old. Somewhere, at some point, the event could happen on its own, and if it does, the result travels outward faster than any signal, faster than any warning, across the entire universe, changing every physical law as it moves. That expanding change has a visual shape and a behaviour that deserves its own full description. If the Higgs field is sitting in a false vacuum, the process that ends it begins with a single point. Somewhere in the universe, a random quantum fluctuation would push a tiny region of the Higgs field over the energy barrier, separating it from the deeper vacuum state below. That region, perhaps smaller than an atomic nucleus, would flip to the new lower energy. The new vacuum value would be different from the current one. The particle masses in that tiny region would instantly recalculate to match the new field strength. Then the bubble forms. Physics dictates that when a lower energy vacuum state appears, it is energetically favourable for surrounding regions of the field to also drop into that state. The boundary between the new vacuum and the old one expands outward. Every point it reaches transitions to the new vacuum. The new particle masses spread with the boundary. The boundary expands at the speed of light. Exactly at the speed of light. There is no faster than light travel in the universe, but the boundary does not need to travel faster. It simply travels at the maximum possible speed, meaning no information about its existence can outrun it. No signal, no warning, no light can escape the expanding edge and reach anything ahead of it. The bubble wall arrives at every location in the universe simultaneously with the first photon that could have announced it. The arrival of the bubble wall is not an explosion in any conventional sense. There is no shockwave, no heat, no visible light. The bubble wall is a change in the laws of physics. The moment it passes through any region, the Higgs field in that region drops to the new vacuum expectation value. Every particle mass shifts to the new values determined by the new field strength. Atoms, which exist because electron mass and quark mass sit at precisely the right values for chemical bonding, instantly lose their structural coherence. Matter as it currently exists dissolves at the bubble wall. Everything inside the old vacuum that the wall has passed through is replaced with matter calibrated to the new physical laws. Whether those new laws allow any kind of structure is unknown. They would be completely different from anything that has ever been studied. The scale of this event is total. A vacuum decay bubble, once formed, does not stop. It has no mechanism to stop. It expands forever, limited only by the size of the universe and the speed of light. The entire observable universe, across a diameter of roughly 93 billion light-years, would eventually be converted. The timeline for any single point is instant. The wall arrives. The physics changes. There is no experience of it. Physicists are careful to separate the terrifying description from the actual probability. Current calculations suggest a vacuum decay event is extraordinarily unlikely on any timescale humans can meaningfully imagine. The metastability of the current vacuum appears to be robust on scales vastly exceeding the current age of the universe. The reason this scenario is taken seriously is not because it is expected to happen. It is taken seriously because the same equations that produced the most successful predictions in the history of physics also predict that the universe might be in this metastable state. If those equations are right about the Higgs boson, they might be right about this too. And if the bubble exists somewhere already, expanding at the speed of light since long before humans existed, the math says we would never know until the wall arrived. What scientists can actually calculate about the timing of this event is the next piece of the picture. The false vacuum decay scenario sounds like pure speculation, but the physics behind it is grounded in real calculations using measured quantities, and those calculations produce something specific, an estimate of how long the current vacuum state is likely to survive. The estimate depends on two numbers above all others: the mass of the Higgs boson and the mass of the top quark. The Higgs boson mass was pinned down after the 2012 discovery. The top quark mass has been measured repeatedly in particle collisions. When both numbers are plugged into the equations that describe the shape of the Higgs field's energy landscape, they determine the height and width of the barrier separating the current vacuum state from the deeper one below. A taller, wider barrier means a lower probability of quantum tunneling per unit of time and per unit of volume. Lower probability means the expected lifetime of the vacuum state is longer. The numbers that have been measured place the universe in a region physicists call the metastable zone. Current calculations estimate the lifetime of the false vacuum at a number so large it makes the age of the universe look like a blink. The figure involves a 1 followed by hundreds of zeros worth of years. The current universe is roughly 14 billion years old. 14 billion is a number with 10 digits. The estimated vacuum lifetime has hundreds of digits. So the decay is not imminent. By any practical measure, the current vacuum is stable for the duration of anything humans would recognize as a timeline. But here is the part that keeps the calculation interesting. The estimate depends sensitively on the measured values of both the Higgs boson mass and the top quark mass. Both measurements carry experimental uncertainties. Slightly different central values within the current error bars move the estimated vacuum lifetime dramatically. Some combinations of measured values within the allowed range push the universe from metastable to fully stable. Other combinations within the same range push it closer to the boundary of instability. The universe sits right on the edge of the stability boundary. That positioning appears exact enough that some physicists suspect it is not a coincidence. A universe exactly at the boundary of stability might be telling us something about the deeper structure of the theory. What that message is remains unread. There is also an external factor in the timeline. The vacuum decay probability calculated by current theory assumes a quiet universe, a region of space with no extraordinary energy concentration, just the regular quantum fluctuations of empty space. High energy events, extremely energetic cosmic rays hitting the upper atmosphere, or even the collisions inside the Large Hadron Collider, could theoretically provide a local energy boost. Scientists have confirmed that particle colliders pose no vacuum decay risk. The energies achieved in the Large Hadron Collider, though enormous by human standards, are far below the energies of cosmic rays that have been striking Earth for billions of years without incident. If collider energies could trigger vacuum decay, nature would have done it already, countless times over. The timeline for vacuum decay, if it ever comes, is written in numbers too large to experience. But the fact that those numbers can be calculated at all, using real measurements and real equations, is itself a statement about the power of the theory. A theory capable of predicting the universe's expiration date, even approximately, is a theory with real content, and that content points directly to something even harder to accept. The measured Higgs mass is not just close to the stability boundary, it sits at a location in the energy landscape that looks extremely unlikely to have arrived there by chance. Return to the number at the centre of the crisis. The Higgs boson has a measured mass of around 125 billion electron volts. That number was confirmed in 2012 and has been refined in every subsequent experimental run. It is one of the best measured quantities in modern physics. The Standard Model predicts that this mass should receive enormous corrections from quantum fluctuations in the vacuum. Every particle that exists contributes a correction. Electrons contribute. top quarks contribute, W bosons contribute. Each correction is calculated using the equations of quantum field theory, which have been tested to extraordinary precision in other contexts. The corrections are real, they must be included. When all the corrections are added, the total is approximately 10 million billion electron volts. The measured mass is around 125 billion electron volts. The ratio between the theoretical correction and the measured mass is roughly 100 million billion. Something is cancelling out that correction to leave behind the small measured value. For the cancellation to work precisely enough, the unknown mechanism must be accurate to about 30 decimal places. 30. If the cancellation were off by even 1 part in 10 million billion, the Higgs boson mass would be wildly different from what is measured. Physicists call this level of precision unnatural. In physics, natural means a number arrives at its value through a reasonable mechanism without requiring specific fine-tuning. The electron mass is natural. The proton mass is natural. The masses of the W and Z bosons are natural, because supersymmetry or the Higgs mechanism provides understandable reasons for their values. The Higgs boson mass, at its measured value, requires either an unknown mechanism doing the cancellation, or an extraordinary coincidence in which the raw mass and the quantum corrections line up to 30 decimal places by accident. Physicists who accept fine-tuning as a real possibility argue that some numbers in nature simply are what they are. Measuring them is the job of physics. Explaining them may be beyond what any theory can accomplish. This view is uncomfortable to many, but it is logically consistent. Physicists who reject fine-tuning argue that the level of precision required is so extreme that it must point to undiscovered physics. Something real is doing the cancellation. It has properties. It can be found. The failure to find it so far is a problem of experimental reach, not a problem of the idea. The hierarchy problem is not merely a technical puzzle. It is a question about the nature of physical law. If a fundamental constant requires 30 decimal places of cancellation to reach its measured value, either physics has a secret that has not been uncovered yet, or the universe is fine-tuned in a way that demands explanation. Every major proposed solution to the hierarchy problem, supersymmetry, extra dimensions, composite Higgs models, has been designed specifically to provide a natural mechanism for the cancellation. Every one of those solutions has either been ruled out in its simplest form or remains without experimental support. The problem is still open, the number is still unexplained, and the deeper the search goes for an answer, the more the proposed solutions start pointing outside the observable universe entirely. In 1998, 2 physicists named Nima Arkani-Hamed, Savas Dimopoulos, and Gia Dvali published a paper with a startling proposal. The hierarchy problem, the enormous gap between the Higgs field's energy scale and gravity's energy scale, might have a geometric solution. Space might have extra dimensions that are hidden from ordinary observation, and those extra dimensions could be diluting the apparent strength of gravity in a way that makes the gap look larger than it really is. The proposal sounds like science fiction. It is mathematical physics, published in a peer-reviewed journal, and it sparked one of the most active research programs in theoretical physics of the last 3 decades. Here is the core idea. Gravity is the weakest of the 4 fundamental forces by an enormous margin. An ordinary refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. The electromagnetic force that holds the magnet to the refrigerator is vastly stronger than gravity across comparable distances. Explaining why gravity is so weak compared to the other forces is itself a version of the hierarchy problem. The extra dimension proposal says gravity is not actually weak. Gravity has the same fundamental strength as the other forces. It simply appears weak because it is spreading itself across additional spatial dimensions that the other forces cannot enter. Imagine water flowing through a pipe. Now imagine cutting holes in the pipe that allow water to leak out in multiple directions. The flow reaching the end is weaker, but only because some of it escaped sideways. Gravity leaks into extra dimensions. The other forces stay in the 3 dimensions we experience. Gravity appears diluted. If this is true, the enormous energy scale where gravity becomes strong, which is what creates the hierarchy problem, is much lower than previously assumed. The hierarchy problem shrinks or disappears entirely. The extra dimensions themselves would be curled up, too small to detect with ordinary instruments. How small depends on the specific version of the theory. Some proposals allow extra dimensions large enough that the Large Hadron Collider could produce their signatures. Collisions at the right energy would appear to create mini black holes, tiny pinches in space-time that would evaporate almost instantly and leave a distinctive pattern in the detector. The Large Hadron Collider has searched for these signatures. No mini black holes have been found. The simplest versions of the extra dimension proposals, with large extra dimensions detectable at current collider energies, have been ruled out. Versions with smaller, harder to reach extra dimensions remain possible. They predict signatures at energies beyond current experimental reach. Like supersymmetry, they remain theoretically alive but experimentally untested at the relevant scales. The extra dimension proposals did something important even if they are ultimately wrong. They broke the assumption that the hierarchy problem could only be solved within 3 spatial dimensions. They opened the question of whether the structure of space itself, not just new particles or forces, might be part of the solution. And if space has hidden structure, that hidden structure might also connect to the most radical idea yet proposed for explaining the Higgs field's exact value. An idea that does not require finding a new particle at all, but instead requires accepting that the universe we live in is only one of an unimaginably large number of universes. The multiverse is not a single theory, it is a family of ideas, some of which emerge directly from established physics, and some of which remain highly speculative. The connection to the Higgs field is one of the most serious versions, and it arose specifically because the field's measured value looks impossibly well tuned to produce a universe capable of containing observers. In the late 1980s, Steven Weinberg, a Nobel Prize-winning physicist, used the cosmological constant problem, a different fine-tuning puzzle related to the energy of empty space, to make a striking argument. He reasoned that if the universe were one of many, each with a different cosmological constant, then only universes with values small enough to allow galaxies to form would contain observers to notice the value. The measured cosmological constant, he predicted, should sit near the maximum value compatible with galaxy formation. When the cosmological constant was measured in the late 1990s, it was close to that predicted range. The argument is called the anthropic principle. Its core claim is that fine-tuned constants may not require a dynamical mechanism to explain them. If many universes exist with different constants, the ones with constants compatible with life are the ones where the question gets asked. Selection bias, not physics, explains the tuning. Applied to the Higgs field, the argument runs the same way. If the vacuum expectation value of the Higgs field varies across different universes in a vast ensemble, most universes would have values incompatible with stable atoms. Observers can only exist in universes where the value sits in the narrow range that allows chemistry. The measured value is not surprising given that it had to be in that range for anyone to be measuring it. This argument is philosophically uncomfortable to many physicists. A good physical theory should predict the values of constants, not explain them away by invoking observers in inaccessible universes. If the multiverse is the explanation, then the hierarchy problem has no solution in the traditional sense. It has an excuse. Other physicists find the argument compelling precisely because the tuning is so extreme. 30 decimal places of coincidence is hard to accept as accident. If a mechanism exists, 50 years of searching have not found it. The multiverse provides a framework in which the tuning makes sense without requiring any new particles or forces. The debate is ongoing. The multiverse is currently untestable. There is no experiment that can confirm or deny the existence of other universes with different physical constants. Some physicists argue this places the idea outside the boundary of science entirely. Others argue that the predictions it makes about what observers should measure, such as Weinberg's cosmological constant prediction, give it partial empirical content. The Higgs field sits at the centre of this debate. Its measured value could point towards supersymmetry, extra dimensions, new particles, or anthropic selection in a multiverse. All of these explanations are currently consistent with the data. None of them is confirmed. The field that gives mass to everything in the universe also carries, inside its measured properties, the deepest unresolved question about why physics has the specific form it does, and that question reaches its most concrete experimental form in the ongoing search for new particles at the world's largest machine, a search that is far from over. The Large Hadron Collider did not stop being useful the moment the Higgs boson was confirmed. The discovery was a beginning, not an ending. Scientists returned to the same machine with upgraded detectors and higher beam energies, hunting for the next layer beneath the standard model. The machine has been upgraded multiple times since 2012. Each upgrade pushed the collision energy higher and the data collection rate faster. More collisions mean more opportunities for rare processes to appear. The rate of Higgs boson production at the upgraded collider is high enough that thousands of them are now created every hour during active runs. Each one decays, and each decay leaves a signature that reveals a small piece of the Higgs field structure. One of the primary targets is the self-coupling of the Higgs boson. Every force-carrying field in physics has a specific relationship with itself. The Higgs field's self-coupling determines the exact shape of the energy landscape, the Mexican hat potential that caused the field to settle at a non-zero value in the first place. Measuring the self-coupling directly would confirm or challenge the shape of that potential and would sharpen the calculation of whether the field is in a true or false vacuum. Measuring the self-coupling requires catching two Higgs bosons produced simultaneously from the same collision, a process called Higgs pair production. It is extraordinarily rare. Producing a single Higgs boson already requires precise conditions. Producing two at once is so unlikely that even with thousands of Higgs bosons created per hour, the pair production events number only a handful per year in the full dataset. The current dataset does not yet contain enough pair production events to measure the self-coupling precisely. The next major upgrade of the collider, planned to increase the collision rate by a factor of 10 and called the high luminosity upgrade, is specifically designed to accumulate enough events to make this measurement possible. That upgrade is expected to complete in the late 2020s. Separately, the collider continues to search for any new particle that could explain the hierarchy problem. The full list of theoretical candidates that have been targeted includes hundreds of different predicted particles across dozens of theoretical frameworks. Each search constrains the properties of hypothetical particles further. The allowed parameter space for most popular solutions has shrunk dramatically compared to before the collider began running. Some theorists argue the shrinking allowed space is itself a discovery of a kind. The absence of new physics at the energy scales probed so far tells physicists something definite. Whatever solves the hierarchy problem, if anything does, is either very heavy, very weakly coupled, or very different from what was expected. That knowledge, even as a negative result, eliminates large swaths of theoretical possibility and forces the field toward new ideas. Other physicists are building proposals for a successor machine. Multiple independent proposals exist for colliders with center of mass energies several times greater than the current machine. These future machines would probe distances inside the proton far smaller than anything accessible today, and could potentially produce particles with masses too high for the current collider to reach. The race is not over. The standard model has a hole in it. The hole has been mapped carefully, and the search for what fills it continues with every collision. The universe did not always have the Higgs field at its current strength. In the first moments after the Big Bang, temperatures were so extreme that the conditions the Higgs field exists in today simply did not apply. The universe was a hot, dense plasma of energy in which the distinctions between fundamental particles were blurred, and the forces that are separate today were partially unified. At those temperatures, the Higgs field did not maintain its current non-zero vacuum value. The field was effectively zero. All particles moved freely at the speed of light. The W and Z bosons, which have mass today because they interact with the Higgs field, were massless at these early temperatures and behaved identically to photons. The electromagnetic force and the weak nuclear force were a single unified force. As the universe expanded and cooled, it went through a series of phase transitions. A phase transition is a change in the state of a system, the way water changes from steam to liquid to ice as it cools. Each phase transition in the early universe changed the structure of one or more fundamental fields as the temperature dropped below critical thresholds. The Higgs field underwent its own phase transition at a temperature corresponding to a time roughly 10 picoseconds after the Big Bang. A picosecond is 1/trillionth of a second. At that moment, the Higgs field dropped from its high-temperature zero state and settled into its current non-zero vacuum expectation value. This transition changed the universe permanently. The moment the Higgs field took on its non-zero value, every particle that couples to it gained mass. The W and Z bosons gained their enormous masses, and the weak nuclear force became short-ranged. Electrons gained their mass. Quarks gained their baseline masses. The electromagnetic and weak forces separated into two distinct forces. The universe reorganized itself in a tiny fraction of a second, from a place where all massive particles were massless to a place where the full hierarchy of particle masses we observe today came into existence. The exact nature of this transition has important consequences for what happened in those first moments. If the transition was a gradual crossover, the universe cooled smoothly through it. If the transition was violent, a first-order phase transition with bubbles of new vacuum forming and colliding inside the older one, the collision of those bubbles would have produced gravitational waves. Ripples in space-time that still travel through the universe today. Current calculations based on the measured Higgs boson mass suggest the transition in our universe was a smooth crossover, but the calculations depend on the precise shape of the Higgs field's energy potential, which is still being measured. A different self-coupling value could push the transition toward the violent first-order type. Future gravitational wave detectors, sensitive to frequencies far below those currently accessible, are being designed partly to search for the signal of a first-order Higgs phase transition in the early universe. Finding that signal would directly constrain the physics of the Higgs field at temperatures that existed a fraction of a second after the Big Bang. The universe's infancy, written in gravitational waves, might still be readable today, and that infancy holds one more mystery. A mystery that the Higgs field may have directly caused. The reason the universe contains matter at all, instead of nothing. The universe should not exist. At least, according to the equations of the Standard Model. When the Big Bang produced energy, that energy converted into particles. But particle creation always comes in pairs. For every particle produced, an antiparticle must also be produced, an electron and an anti-electron, a quark and an antiquark. Equal amounts of matter and antimatter, created together, cancelling each other out completely if they meet. A universe that begins with equal amounts of matter and antimatter ends with nothing. The pairs annihilate, all energy converts back into radiation. No atoms, no stars, no planets, no people. The observable universe contains matter. Almost exclusively matter. Whatever process created the universe produced more matter than antimatter. At least one extra matter particle for every billion matter-antimatter pairs. That tiny excess survived. Everything we can see is made of it. Physics has a name for the mechanism that created this imbalance. Scientists call it baryogenesis. They know it happened, they do not fully know how. For baryogenesis to occur, three conditions must be met simultaneously. Matter and antimatter must behave slightly differently from each other. The universe must go out of thermal equilibrium at some point. And processes must exist that produce more matter particles than antimatter particles. All three conditions were identified in the 1967 by Andrei Sakharov. They are confirmed as necessary. Whether the Standard Model actually satisfies them strongly enough to produce the observed matter-antimatter imbalance is a different question, and the answer appears to be no. The matter-antimatter difference built into the Standard Model, called charge parity violation, is too small by many orders of magnitude to account for the surplus of matter we observe. Some additional source of asymmetry is required. The Standard Model does not contain it. The Higgs field enters this problem directly through the phase transition it underwent in the first fraction of a second, a violent first-order phase transition where bubbles of the new Higgs vacuum formed and expanded would have created regions of space out of thermal equilibrium at the bubble walls. These out-of-equilibrium regions are exactly the environment where an enhanced matter-antimatter asymmetry could develop. Extensions of the Standard Model that predict a first-order Higgs phase transition and introduce new sources of charge parity violation are actively studied as explanations for baryogenesis. They are called electroweak baryogenesis models. The Higgs field in these models is directly responsible for the fact that the universe survived. Whether this happened depends on the Higgs field's self-coupling and the shape of its energy potential at high temperatures. The same measurement that would clarify the vacuum stability question, the direct measurement of the Higgs self-coupling, would also constrain whether the early universe experienced the right kind of Higgs phase transition for electroweak baryogenesis to work. A single measurement, planned at the next generation of colliders, could connect the stability of the current universe to the survival of the early one. The Higgs field may be the reason matter exists, and it may still hold the answer to whether that matter will last. The phase transition of the Higgs field was the pivotal moment in the early universe's history. Everything that came after it, every atom, every star, every galaxy, traces its structure back to that brief window when the field settled into its current value. But the transition itself, and the conditions immediately before and after it, raise questions that extend far beyond what the Standard Model can currently answer. Before the Higgs field settled, the symmetry between the electromagnetic force and the weak nuclear force was exact. Both forces were the same. The particles that carry them were all massless. The distinction between different types of quarks and leptons was less sharp. The universe was a hot, symmetric soup. The moment the Higgs field dropped to its non-zero value, that symmetry was broken. The W and Z bosons, which carry the weak force, became heavy. The photon, which carries electromagnetism, remained massless. Two forces that were one became two different forces with vastly different ranges and strengths. The particles of matter, quarks and leptons, took on their distinct masses. The periodic table of elements became possible. Everything that makes the material universe complex, including chemistry, nuclear physics, and the possibility of biological life, was unlocked in that transition. Understanding the precise details of this transition requires knowing the full shape of the Higgs field's energy landscape at high temperatures. The Mexican hat shape that describes the field today changes as temperature rises. At very high temperatures, the hat shape flattens. The displaced low points that the field currently occupies move toward the centre. At the critical temperature, the brim and the centre are at the same height. Above that temperature, the central point becomes the only minimum, and the field sits there at zero. Physicists can calculate this temperature-dependent landscape using the measured properties of the Higgs boson and the top quark. The current calculations say that in our universe, the transition from the symmetric zero-field phase to the broken non-zero phase was a smooth crossover. The field did not snap suddenly from zero to its current value. It rolled gradually as the universe cooled. A smooth crossover is less dramatic but more stable. It does not produce bubble collisions or strong gravitational waves. It produces a universe that transitions quietly into the matter-filled, mass-rich state we observe. But the word currently is doing real work in that description. The calculations use the measured Higgs self-coupling, which is not yet directly confirmed. If the self-coupling is slightly different from the value assumed by current calculations, the nature of the transition changes. A stronger self-coupling could push the transition toward a first-order type, with bubble formation and violent dynamics. Future gravitational wave observatories, sensitive to frequencies in the millihertz range, are planned partly to detect the gravitational wave background that would have been produced by a first-order transition. If that background is found, it would be direct observational evidence of the Higgs phase transition itself, a snapshot of the universe at the moment the field turned on. Finding or not finding that signal would simultaneously tell us about the early universe and about the current stability of the vacuum. The physics of 14 billion years ago and the physics of today are written in the same equations, and the measurement that connects them is now within reach of the next generation of experiments. The Higgs field was the hinge on which the early universe turned. It may also be where the next revolution in physics begins. The Higgs boson discovered in 2012 matches the predictions of the simplest possible version of the Higgs mechanism. One field. One boson. One vacuum expectation value. Physicists call this the minimal standard model Higgs sector. Minimal does not mean correct. It means the smallest assumption that fits the current data. Most theoretical frameworks that attempt to solve the hierarchy problem, explain dark matter, or account for the matter-antimatter imbalance predict that the Higgs sector is not minimal. They predict that additional Higgs fields exist, each with its own boson. Some predict 2 additional neutral bosons. Some predict charged Higgs bosons. Supersymmetry in its minimal version requires 5 distinct Higgs bosons. The discovered boson, the one sitting at around 125 billion electron volts, would then be the lightest member of a larger family. The heavier siblings would have distinct masses and decay patterns. Finding them would immediately identify which theoretical framework beyond the standard model is on the right track. The Large Hadron Collider has searched for additional Higgs bosons across a wide range of masses. No second boson has been found. The searches have excluded specific mass ranges for specific types of additional bosons, but large regions of the theoretical parameter space remain unexplored. The reason additional Higgs bosons are so interesting goes beyond simply extending the particle count. A second Higgs field with its own vacuum expectation value would interact with the first one. The interplay between 2 Higgs fields can produce effects that a single field cannot. It can introduce new sources of charge parity violation, which is what baryogenesis requires. It can modify the shape of the Higgs energy landscape in ways that make the electroweak phase transition first order. It can provide a natural dark matter candidate in the form of a stable neutral scalar particle. A second Higgs boson, if found, would solve multiple open problems simultaneously. The search for it continues with every data taking run of the collider. Physicists look for signatures in decay patterns, in the rates of Higgs boson production, and in the detailed shape of the distributions of particles produced in high-energy collisions. Deviations from the standard model predictions, even tiny ones, could signal the presence of additional Higgs fields influencing the physics through quantum corrections. So far, all measurements of the discovered Higgs boson are consistent with the minimal standard model predictions. The coupling strengths match. The decay rates match. Every property measured matches the simplest possible Higgs sector. That consistency is itself a puzzle. Either nature chose the minimal option, which would be unusual given how often simpler descriptions of nature turn out to be incomplete, or the additional Higgs bosons are heavier than current measurements can detect, or they couple to ordinary matter weakly enough to hide in the current datasets. The next generation of collider experiments, with higher energies and vastly larger datasets, would extend the search into mass ranges and coupling strengths that the current machine cannot access. If additional Higgs bosons exist anywhere in the theoretically motivated mass range, the next generation of machines would find them or rule them out definitively. What finding a second boson would mean for physics is almost impossible to overstate. The entire theoretical landscape would reorganize around the discovery. Decades of competing frameworks would either be confirmed or eliminated overnight, and the deepest questions about the Higgs field would suddenly have a new set of tools to answer them. The standard model is the most successful scientific theory ever written down. That statement is not an exaggeration. Its predictions have been tested against experiment across dozens of measured quantities, some to more than 10 decimal places of precision, and have matched reality at every point. No experiment has produced a result that clearly contradicts the Standard Model's predictions, and yet physicists speak openly about wanting to break it. Breaking the Standard Model does not mean proving it wrong in the way that replacing a discredited idea means. The Standard Model accurately describes physics in the energy ranges that have been tested. Whatever replaces it or extends it must reproduce every result the Standard Model already explains. The Standard Model is not going to turn out to have been a mistake. It is going to turn out to have been an incomplete picture of something larger. The history of physics is full of exactly this pattern. Newton's mechanics described motion with extraordinary accuracy for over 200 years. Einstein's relativity did not invalidate Newton's equations. It revealed the deeper framework inside which Newtonian mechanics is an extremely accurate approximation at low speeds. Quantum mechanics did not invalidate electricity and magnetism. It revealed the underlying rules from which those classical equations emerge. The Standard Model will be extended, not discarded. The question is what the extension looks like and what new understanding it brings. Finding new physics at the Higgs mass scale through a second boson, a superpartner, an extra-dimensional signature, or any other deviation from the Standard Model predictions would reveal the form of the extension. It would tell physicists which of the many proposed frameworks is on the right track. That single data point could eliminate hundreds of competing theories and focus the entire field on the correct direction. The impact would reach every branch of physics. Cosmology would gain new tools to understand the early universe and the nature of dark matter. The matter-antimatter problem might find its resolution. The stability of the Higgs vacuum would be calculable with new precision. The full shape of the Higgs energy landscape would come into view. The technology that emerges from deeper understanding of the Higgs field is harder to predict but historically inevitable. Every fundamental advance in physics has eventually produced technologies that transformed daily life. Quantum mechanics produced transistors, lasers, and memory machines. Nuclear physics produced power generation. The Standard Model itself, developed to understand particles, gave rise to the World Wide Web as a tool for sharing the massive datasets it generated. What understanding the deeper structure of the Higgs field will produce is unknown, but the gap between the current framework and the full truth of physics is large enough that the tools required to bridge it would almost certainly introduce concepts and capabilities that are presently unimaginable. The Standard Model works, it is also incomplete. That combination means physics is standing at the edge of its next major transformation. The Higgs field is where that edge is sharpest. And the final question is not what we will find, but why the field matters more than anything else currently being studied. Everything traced back to it. Mass, chemistry, the structure of atoms, the shape of the forces that govern matter, the reason the universe contains something instead of nothing, the stability of the vacuum that the universe has been resting in for nearly 14 billion years, the phase transition that switched the cosmos from a structureless plasma to a world where particles have distinct identities and distinct weights. Every one of those things traces back to the Higgs field and the single number it maintains everywhere, at every moment, across every inch of the observable universe. The Higgs field is the most important unsolved problem in physics today, not because it is poorly understood in an abstract way, because the measurements made in the last decade have placed it at the intersection of every major open question in the field simultaneously. The hierarchy problem asks why the Higgs boson mass is small. The vacuum stability problem asks whether the universe is resting on a permanent foundation or a temporary one. The matter-antimatter problem asks whether the Higgs phase transition explains our existence. The dark matter problem asks whether the invisible mass filling the universe couples to the Higgs field. The neutrino mass problem asks whether the Higgs mechanism covers all massive particles or leaves something out. Every single one of these open questions has a thread that runs directly into the structure of the Higgs field. Solve the hierarchy problem, and you likely understand the field's stability. Measure the self-coupling, and you learn whether the early universe created a matter surplus. Find dark matter, and you discover a new sector of Higgs interactions. The Higgs field is not a solved chapter of physics sitting in the textbooks. It is the active frontier. The machine still running underground in Switzerland is still collecting collisions. The upgrade that will measure the self-coupling directly is being built. The gravitational wave observatories designed to detect the remnant signal of the Higgs phase transition are in development. The field discovered in equations in 1964, confirmed experimentally in 2012, and now revealed to be the pivot point of every major crisis in modern physics, is still giving up its secrets one measurement at a time. Peter Higgs spent 48 years waiting for the boson to be confirmed. He lived long enough to see it. He did not live long enough to see what the boson revealed about the field bearing his name, that it is far stranger, far more unstable, and far more central to the nature of reality than anyone suspected when he wrote his equations in Edinburgh more than 60 years ago. The field is everywhere. It is always on. It holds the mass of every particle in your body in place at this exact moment. It determined the shape of every atom that ever formed. It may have been the reason matter survived the first second of the universe, and according to current calculations, it is sitting at an energy level that physics cannot yet fully explain, in a state that may be permanent or may be temporary, and in a configuration that implies something beyond everything currently understood is waiting to be found just past the edge of what the most powerful machine ever built can reach. The field beneath everything is still speaking. Physics is still learning to listen.